All right, I told you we're going to get formal. So now we're going to formally derive what we've been using. We've been working around this, and now you're going to get derivation. Why is kinetic energy 1/2 mv squared? I mean, why not mv squared or just m times speed or whatever? Let's check it out. Okay, so what we're going to do now is, and my students in my class know that this will probably be on an exam, and they'll probably get 10 to 15 points if they can reproduce this. Okay, we're going to do this in two parts. So we're doing the mechanical work energy theorem. Remember, mechanical has to do with kind of bulk motion, right? It's the work kinetic energy theorem, form 1. And we're going to, out of this little derivation, very quick, you're going to get the definition for work and kinetic energy. We'll explore work later in later videos. So what we've done, remember that, and hopefully you remind yourself how to do this, it's on a video, kinematic analysis and force analysis, Newton's laws, right, can be turned into momentum analysis. Pretty quick sleight of hand. Remember, the beauty of that is that the forces of interaction can be messy. The time of collision, the way that happens, collisions, explosion, very useful. But it's really kinematics and force analysis in disguise. Now, we're going to take kinematics and force analysis and create energy analysis as promised. In this video, we'll derive in a simple case, so it's not too formal, it's just a little bit formal, form 1, okay? And that's useful. And we'll obtain the mathematical definition for kinetic energy and work, what we mean by mechanical work or work from a force. In the next video, we're going to get to the form that we've been using, the energy accounting. See, we're going to rearrange this that we get in this video, and we're going to find the mechanical work energy theorem, where mechanical energy is kinetic plus potential energy. I call it form 2. It's the one we really use. It's a very useful way to look at it. Form 1 in some way sort of fundamental, but this is how we think of it. This is our energy accounting. We've done this some, but we're going to add this concept of work in here. The definition for change in potential energy is going to come out of this, and that's for any conservative force. We're going to get that in the next video, and I'll define that clearly. Then we'll find specific change in potential energy for specific conservative forces, and then you'll go on, when you do electric force, it's going to be important as you go circuits and things like that. We'll look at the relationship between force and potential energy in the integral form and the derivative form. So that's coming up, but right now it's going to be a quick video. Make sure that you can do this, all right? So if you have in your mind an outline of the steps, it's just mathematical. We're just going to do a little magic trick with kinematics and force analysis and redefine things. If you have in your mind an outline of the steps, you know you can always do it. Check it out. First, the physics. Recall, net force parallel to a velocity will do what? It will increase the speed of an object, right? And that is synonymous in energy language, translating to energy language, that's synonymous with increasing kinetic energy. Net force opposite velocity will, of course, decrease the speed and so decrease the kinetic energy. Net force perpendicular to velocity only turns an object, and since energy is not a vector, it is a scalar. Does that change? No, it doesn't change the kinetic energy at all. It just turns it. That's very important when we do magnetism too, and a variety of things. So there's some deep stuff, cool stuff here. Keep that in mind. It's not bad, right? So just keep building on that. So here's the steps. I want you to pause after we go through these steps and fill them in. And then come back and I'll do them one by one. And so try to get at least one step and then come back and see if you did it. I want you to write Newton's second law first. Just straight up Newton's second law in vector form. Then turn it into a one-dimensional. This will be quite adequate for getting the essence of what we're doing. So make it one-dimensional, say the x direction. Then assume that the acceleration is constant, which means the net force is constant. Okay? Again, for this quick derivation, it works wonders. You can look up for more general derivations elsewhere if you want. Then we simply rearrange, and we rename and reinvent or invent some terms. Okay? So pause now and start with Newton's second. Write it as only x components. Put in constant acceleration. Good? Okay. So now you've paused. You're back. Again, I want to warn you. If you're just watching, That might get you a C in a class. If you're watching and reading, again, a C. If you're just doing problems, I suspect maybe just a C, you aren't getting all the insight. You need to do both. This is complex stuff. It's powerful, it's good, it's worth it. So make sure that you do pause and scratch your head and just sit with it, struggle with it for a while, because you're actually making some connections in your brain when you do that. Go ahead and pause if you didn't the last time. All right, now we're back. Newton's second law. All right, what is Newton's second law? Well, it is that the net force from others, you know I like to call them sources, on, I like to call it the receiver, object R, the net force causes that receiver, the receiver resists acceleration, but the net force causes the acceleration vector of R. That's Newton's second law, right? Now in 1D, so let's do this in one dimension, all right? Fine, one dimension, then just again to make this a clean, simple derivation. So that's going to be F net x component, and I'll just say on R. We know that there's got to be some sources, someone to blame. Force always has someone to blame. Equals mass A R x component. Fine. This is not a force because there's no interaction here. That's just what happens because of those interactions. Good. Now pause. What do you know about, what do you know about constant acceleration? How can I redo this? What do you know acceleration is with the kinematics? Now we're going to pull in some kinematics here. You back? Okay, good. You tried that out. Constant accel kinematics. Remember that one? VL squared equals V E squared plus 2A delta x, and that's AX really, right? And of course these are really the x components if you want to be picky about it, which is a good thing. And so what does that mean? AX is equal to V later x squared minus V earlier x squared divided by delta x and divided by 2. Only put the 1/2 out here. Everybody see that? You're cool with that? Fine. That looks good. So I'm going to say that that is equal to mr times 1/2 times that mess, VL, I could drop the x, but let's just keep it in there, V earlier x squared over delta x. All right, so now if you've had a sense of energy, maybe you'd like to rearrange that and see if you can guess where we're going. All right, now I'll do it. So let's give that a shot. Hey, I'm gonna mess with this. I'm a theoretician now, right? I got no equipment here. So I'm gonna say, the F net x component on this object R times delta x is equal to, I'm gonna rearrange this too, right? 1/2 mr VLX squared minus V earlier x. Looking interesting here. What is, I could do that like that, or I could do a little algebra. 1/2 mr VLX squared. It's a little harder to write it this way, but I'm just going to go and explore this possibility. V earlier x squared. Now, if it's only moving in the x direction, I don't really need these components, right? I mean, it's just doing that. And we can generalize, and we can do that in y, and I showed you a little bit about that when we were doing the 2D projectiles. But we've done it. We've done it. What have we done? What have we done? What we've done is we've created the form 1 of the work energy theorem. That's it. Look, Newton's second law. Let's just keep it simple, right? 1D, constant acceleration. So Newton's second law, put this guy in there, which came straight from the definitions, right? And the assumption of constant acceleration. Put it in there, rearranged, and what is this called? This is called the net, or total, because network? I don't know. Work on R, or to R, okay, is equal to, and I'm going to rename this guy. What's that? I don't know, kinetic energy later, minus, what's this guy? Kinetic energy earlier. So I can write it like that, or heck, why not use some shorthand? And that's of the receiver. And that is it. That's the derivation. We have invented a new way of talking about kinematics and force, a new way of analyzing motion, a new way of predicting the future in simple setups, or deducing the past. Hey, if this is the case now, what happened in the past? We can use energy. And this is energy accounting, but I have no potential energy in here because it's hidden in here. And that's the next video. We're going to move this around a little bit more and use that beautiful form that we use for energy accounting. And that goes just so far, and it doesn't have to be mysterious. Keep in mind that behind the scenes, we've done this. Okay, we've made these moves. So make sure you can do that, practice it, and on to the next one. Do it yourself though. Make sure that you pause and you can do it yourself on paper, and not just with short-term memory. Wake up about 2:30 in the morning and see if you can do it from a dead sleep. All right, until next time.